In this sixth module, we are discussing weak interaction, and in this fourth video, we discuss a prototype process of charged weak interactions, the leptonic interaction of the W boson. After following this video, you will know how to describe the decays of muon and tau leptons in terms of a Feynman diagram, and how to discuss the properties of this interaction quantitatively. Here is the Feynman diagram for muon decay. The emission of the W- converts the muon into a muon neutrino. The virtual W then decays into an electron-electron antineutrino pair. This way, the lepton number, weak isospin, and other quantum numbers are conserved. In the diagram, we already converted the outgoing antineutrino into an incoming neutrino by inverting its charge and for momentum K' into minus K'. In the amplitude, the W propagator contributes a factor of 1 over Q square minus the mass square of the W, which weakens the amplitude for Q square much smaller than the square of the mass of the W. At low momentum transfers, like for light particles decays, where Q square is smaller or equal to the square of the mass of the muon, that is negligible, the propagator is constant and equal to the inverse of the square mass of the W. We can then treat this process in the so-called Fermi approximation. By convention, one absorbs this residue of the W propagator with the square of the coupling constant G square to form the Fermi constant Gf. It takes the role of the fine structure constant for weak interactions. In this approximation, valid at low momentum transfers, weak interaction can be described by a direct interaction between two current densities. The transition currents corresponding to charged weak interactions are similar to the electromagnetic ones. One denotes them in an imprecise manner as charged currents, Cc. Analogously, the interaction of the Z boson at low energy, that is Q square much smaller than the square of the mass of the Z, can be approximated by direct interaction of two neutral currents N and C. The constant ρ involves the Weinberg angle θW, which measures the ratio between the coupling constants of the weak charged and neutral interactions. The constant ρ is equal to 1 with good precision. This is due to the fact that in the standard theory of electroweak interaction, the masses of the vector bosons and the coupling constants are connected by the Higgs mechanism, which we will discuss in video 6.11. High precision experimental results verify this relationship. The differential muon decay rate, neglecting the mass of the electron, which is much smaller than the mass of the muon, is given here as a function of the energy E' of the outgoing electron. This energy can vary between 0 and half the mass of the muon. As this process is virtually the only decay channel, the total rate is obtained by integrating over E'. The measured lifetime of the muon is close to 2.2 times 10 to the minus 6 seconds. We thus find a Fermi constant of Gf of about 10 to the minus 5 inverse Gv squared. The factor m to the 5 comes in through the phase space factors, which enter into the calculation of gamma. Therefore, we find the same formula for other weak decays, especially for the tau decay. It does, on the other hand, not directly correspond to the total decay rate because the tau has other important decay channels due to its large mass. So gamma for this specific decay is just a partial width. We must take into account the branching fraction in the numerator. One of the most precise experiments that measured the muon lifetime is Muon at the Paul Scherrer Institute of Villingen in Switzerland. A mu plus beam enters from the left and is stopped in the target. The scintillator ball surrounding the target registers the positrons from the decay and measures their emission times. The number of decays per unit time follows an exponential law to a very good approximation, with a low background from accidental coincidence between beam arrival and the electron signal. The slope of the curve gives the muon lifetime. The Muon collaboration finds a value of 2,196,980.3 plus minus 2.2 picoseconds. These results dominate the global average of the particle data group. This gives a value of the Fermi constant accurate to 0.6 parts per million. The tau lepton lifetime is too short for a direct measurement. We rather measure its path length L at high energies. Tau leptons are produced in large numbers in electron-positron annihilation into tau pairs. At high energy, that is the square root of S equal to twice the energy of the tau, their lifetime in the laboratory frame is extended by the relativistic factor gamma. Their mean path length L is therefore longer by a factor p over the mass of the tau. With a lifetime of several hundred femtoseconds, the path length itself is hardly directly observable even at high energies. At a tau energy of 50 GeV, for example, the average decay distance is about 2.5 millimeters and thus completely contained in the vacuum tube that contains the beam of a collider experiment. One determines the decay point from the vertex of decays into three charged particles, as the tau decays in 3 pions plus a neutrinos. The trajectories of the 3 pions are measured with a tracking detector, which is typically a silicon detector, directly outside the vacuum tube. They are then extrapolated back to their common origin, which is the decay vertex of the tau lepton. The tau origin being known from the beam position, the decay length L is thus the distance between the 2 points. The decay length distribution in logarithmic scale shows the expected exponential behavior, but modified by the experimental resolution, which is significantly worse than for direct time measurements. The slope of the distribution measures the average decay length, which in turn gives the lifetime as L divided gamma b. The global average tau lifetime, determined by the particle data group, is 290.3 plus minus 0.5 times 10 to the minus 15 seconds. This figure is in excellent agreement with the prediction based on the Fermi constant, as determined by the measured lifetime of the muon. This shows that the coupling constants of the electron, muon, and tau to the W boson are the same to within a few per mil. In the next video, we'll talk a little more about the properties of the W plus and W minus bosons, and in particular about their masses.